So what will you hear about today? First, I want to talk about the motivation, why to do such a project, then a little bit on the technical background of it, the methodology, what I use to accomplish my tasks, what output did I gain from my tests, and then I want to provide an outlook on how this project proceeds. So first to the motivation. Here at the Space Research Institute in the Magnetometer group, we deal with the implementation of spaceborne flux-gate magnetometers. So these are magnetic field instruments that use electronics, and to provide little weight, little power, we need the miniaturization of exactly those electronics. So for this purpose, a mixed signal application-specific integrated circuit, or in short, ASIC, was developed in cooperation with the Graz University of Technology, with the Institute for Electrical Measurement Systems. All of this project was funded by the Austrian Research Promotion Agency in the Austrian Space Applications Program. And with our ASIC, we hope to develop instruments that are capable to fly on CubeSats, like the one that you can see in this picture. So here, this CubeSat is a 6U CubeSat, so approximately this size, with a magnetometer boom that contains a sensor in the front. So this is a typical flux-gate arrangement. So what is now a flux-gate? Let's dive into the sensor principle here on the left. So basically, we want to measure magnetic fields. Here on the left, you can already see we have a soft magnetic ring core. Everybody probably will recall the BH curve. So this soft magnetic ring core is excited by an AC current or an AC magnetic field and driven into saturation. So basically, we walk up and down on this curve, going on the left side and on the right side symmetrically into saturation. Now, if an ambient magnetic field, like the one blue vector here, is present, all of this excitation shifts, and basically on this curve, we are asymmetrically moving along. So we have an asymmetric saturation in both of the arms. And this exact asymmetry we can pick up with a sense coil. So this sense coil outputs a signal that is 2 times the frequency of the excitation, and the amplitude of this signal, it moves monotonously with the ambient magnetic field. So the more ambient field, the more signal on the sense coil. So as this only is monotonously, but inherently nonlinear due to the nature of the ring core, we add another coil that provides feedback. So with this feedback coil, we compensate exactly the external field to get an internal field of 0. And this can be done in a very linear manner. So we can get a very linear measurement out of such a flux-gate sensor. So now that you know how the sensor works, let's have a look at the electronics. So this is basically how we build a flux-gate instrument. Here we have an FPGA. It is a programmable logic chip. This FPGA drives excitation electronics, which provide the excitation to the flux-gate sensor. From the flux-gate sensor, we get the sense signal, which is amplified, demodulated, digitalized, and fed back into the logic circuit. Within the logic circuit, we run a compensation algorithm that calculates exactly how much current to put out through another digital to analog converter, so the other direction, and a current amplifier to provide the exact feedback, which is exactly the same as the ambient magnetic field. So this value provides our digital measurement value. So where does the chip come into play? All of these analog functions here, everything except for the excitation. So amplification, the interface between analog and digital values, everything happens on the magnetometer front-end ASIC that we develop. So you can probably guess it's with this arrangement, with the compensation and going to zero, the measurement performance of the whole instrument is determined by how good is the quality of our feedback signal. So the digital to analog converter and the current source provide the instrument performance. So this will also be the test subject of this. This was the test subject of this project. So let's have another look at the chip. Here you can see a diaphoto. So this is very zoomed in. In reality, this is only 3 millimeters by 1.5 millimeters. And you can see all the electronic structure on the chip. A few facts to it. It was manufactured in a 180 nanometer process. So this describes how big are basically the transistors which are manufactured on there. It contains a specialized digital to analog converter, which is fed through a low voltage differential signaling interface. We do this to keep noise down and to provide high-speed communications to the DAC. We feed it with a 10 kilohertz signal, but we output a 1 megahertz signal. So to accomplish this upsampling action, we've implemented a so-called cascaded integrator cone filter, which basically multiplies the sample rate in our case. The DAC itself is of a current steering type. So you have multiple cells which are switched on and off to provide more or less current. And we also have a specialized technique called dynamic element matching. I will get back to it later. It is basically it is used to provide a better linearity for the component. And additionally, we also have an amplifier for the current. This was a very good development of Theo Graz, the so-called Howland current-controlled current source, which provides the feedback current to the Fluxgate sensor. So much about the Fluxgate. Let's talk a little bit about radiation. So when we characterize electronics in terms of radiation, we basically expect two different occurrences. One are the single event effects. Those only happen once in a while. So when ions penetrate a silicon semiconductor, several of these single event effects can happen. One of them, the most bad of them, I would say, is the so-called latch-up. In this case, the supply lines of the chip are shorted. This, depending on the chip, this may or may not lead to destruction of the component. Usually, they are not destructed. And such a latch-up can be reset by turning off the supply and turning it back on again. Otherwise, there can also happen signal disturbances, be it either in the analog or in the digital domain. So in the analog, when a particle penetrates, it generates charge and it disturbs an analog signal. These disturbances can also cause a digital bit to flip. So there is some distinction in between there. And in a bad case, these disturbances can also lead to a functional interrupt when the function ceases to work. So to quantify radiation, to make use of it for single event effects, we have two parameters. One is the fluence, describes basically the total number of ions going through an area. So you have some type of flux, and you count all of the ions that go through a specific area. And the other one is about the particles themselves. It's the linear energy transfer. It's a description of how much energy is in the particle, but it's specialized to the ion penetration occurrence. So when an ion penetrates the silicon semiconductor, it transfers energy to the silicon lattice. And this can be measured in how much energy is transferred per unit length. So it's joules per centimeters or mega electron volts per centimeters. But you will probably notice that this doesn't work out with these units here. So usually in semiconductor technology, you also norm this value to the density of the material. So you can compare it to other types of semiconductors like gallium arsenic or germanium. Yes, so this about the single event effects. The other things that can happen or that we expect are total ionizing dose effects. So these are not occurrences that happen once, but they accumulate over a certain dose of radiation. We can get analog parameter degradations, or in the digital domain, timing shifts or supply current increases. So here we quantify the radiation in terms of the total ionizing dose. We have a special non-SI unit here. It's the rad. It is specific to these physics. It's basically 100th of a gray, which is 100th of a joule deposited into 1 kilogram. Okay, so much about the background. Let's dive deeper into the project and what we did. So first we wanted to look at single event effects. And to do that, I made myself familiar with the energy transfer process. And here I've run simulations about heavy ion penetration. So there's an old program available. It's called SRIM. And here, if you look at a chip, you have not only the p and n doped regions on the chip, but you also have metallic connections in between them. Also isolation in between them, and there's a whole stack of layers on top of the so-called active region, which interconnects the components of the semiconductor and makes it work basically. So you can guess if an ion penetrates this, though all of those different materials prove some different resistance to the ion, and a different amount of energy is transferred at each layer. So with this program, I could run simulations of all of these layers with different materials and how much energy is transferred at each of these layers. So here in red, this is the so-called active region. This is the region that we are most interested in, because exactly here happens the semiconductor magic, let's say. So these simulations help to understand how much energy is transferred to a chip, and what, in turn, also how many charge does this mean in the electric circuit. Okay, so after those simulations to test for the single event effects, I built a specialized hardware. You can see a picture of the so-called radiation board here. It holds the DUT, the device under test, or the in this case the magnetometer front and ASIC. And this is mounted inside the irradiation chamber where the beam will be fired at the DUT. Such irradiation chambers are mostly closed, so you have some type of feed-through where you can connect another hardware. In this case, we had this so-called adapter board, which handled all of the digital functions and data logging. And everything was controlled by an external PC. So for the heavy ions test, we went to a test facility in Belgium at the Catholic University of Louvain at the Cyclotron Resource Center. This is an ESA-supported facility, which basically serves as the industry standard for those single event effect tests. I've acquired the funding through a program called RadNext. They try to connect all of irradiation facilities all across Europe and provide to experimenters like us the capability that we can run our tests. So for this facility, I used the simulations that I've shown you before to take all of the available ions with their energies and calculate how much linear energy transfer can we achieve inside the magnetometer front-end ASIC. Here's also another picture where we have the radiation board mounted with the DOT. All of this fixture here, it moves inside a chamber, which is then evacuated. So everything was also done under a vacuum, and very interesting project to carry out. So with everything in place, we could fire up the cyclotron and have our heavy ion beam shooting at the DOT. And what did we measure there? So we saw three very prominent effects. We measured the output current of the chip, so the one that does the feedback. So the first single event effect we saw were spikes on ions hit. We could not exactly determine if this was happening in the analog or in the digital domain because we could only measure the output current, which is made up of a chain of both elements. Then we saw steps. Those steps, we could definitely say that they must happen in the digital domain because there we have the cascaded integrator cone filter, and it integrates a digital value. So when the input value comes one time, this manifests in the integrator output and it persists. And another thing that we saw were functional interrupts, where the output current went back to zero altogether. We could see a very distinct pattern. It was always the same pattern. So with more research on that, we could probably pin down the exact component that was affected there. But most of all, what is the best result that we could get out of this test is that we did not see any latch-ups. So basically, this means for our semiconductor technology, it is very suitable to be used in space, and we do not have to take any precautions to make it radiation hard in terms of latch-up. Okay, so we not only looked at how do these effects look in the output current, but also how often do they occur. So out of all of these effects, 82% were spikes, 13% were steps, 4% were those functional interrupts, and less than 1% was a combination of all of those three. So with these statistics, you can calculate the parameter. It's the so-called single event cross-section. So it's basically, you remember, we have the flux, like ions per area. So if we assume that every ion causes a single event, then we can calculate an effective area or an effective cross-section of the chip that would be basically how the chip responds. So the bigger this cross-section, the more single event effect happens per flux. So here you see this statistic, and usually you can fit a so-called Weibull function to that. It has two very important parameters. One is the threshold LET. It's basically at which LET do you start seeing single event effects, and the other is the saturation cross-section. It's basically if you move up in LET, the cross-section does not change more then up to the saturation cross-section. Okay, so these were the results of the single event effects test. Let's move on to the total ionizing dose test. So usually it is, or professionally, I would say, it is done using like a real nuclear source like cobalt-60. But the same effects as, for example, the cobalt-60 source can provide can be accomplished by the use of X-rays. So also do that, the TU Graz is right around the corner. We went there and did the total ionizing dose tests with their X-ray facility. So they have this chamber. You can put your test setup or your DUT inside there, close the door and run the X-ray tube, which outputs a X-ray beam. And so with all of this big radiation board, we went in there, but we had to protect all of the electronics that were not the DUT. So I built a sheeting to put around that and only expose the DUT. This was made of 6mm steel, so it kept out all of the X-rays from the rest of the electronics. And additionally, when you look at the X-ray tube, the beam comes out here, and you have to calibrate what is the dose rate at your distance here. And you also have to align so that your DUT is in the middle of the beam to get the most uniform irradiation. So this we could do with such a phosphorus plate, which illuminated when it was hit by the X-ray. So this was looking very nice. Okay, so what did we measure in this test? We applied a certain dose of irradiation. So the RAPs that I told you before, in this case, kilowatts. And then we measured on the output current the gain and offset characteristic, and also how the output current spectrum looks like. So it's basically at certain frequencies. Do we see any sinusoidals, even if we output a DC value? So what could we measure there? For one, we could see a slight degradation in the gain. The gain here, it's between the digital value and the analog output current. And here you can see for sample 1, 3, and 4, I've made a fit. This blue line, this fit is kind of a special case because it does not explain the exact effect. It only explains the worst case. So you can see the degradation comes down and goes back at some point. And this also happens at not every time the same point, but also sporadically. So with this fit, we have like a worst case estimation if we plan for a mission that we can say, okay, at worst it will be that, probably better, but okay. And one other thing that was very interesting in this test is that one sample showed only about 1/4 or 1/5 of the effects of the other samples. So I don't know where this outlier comes from, but we could observe it. Also in the offset between the digital and the analog value, we could not make out a very distinct pattern that we could fit a function to, but we can see that the spread in those 3 samples is also much greater than in sample number 2. So much about the gain and the offset during irradiation. One effect that could be seen was in the output current spectrum. So I told you before about the dynamic element matching. So it is a technique where you have several several current elements which are combined to form a sum of a current, and those are not exactly matched. So to get better linearity, you take more of these elements and you randomly distribute your output value across these current elements, and you get better linearity, but you also get some tones in your output spectrum. And here it is very interesting. You can see in the topmost plot, you see those spectral lines which correspond to such a dynamic element matching tone. And as you irradiate the chip, the distribution of the mismatch between the current elements changes. So you can see that also the output spectrum, you see spectral lines, they change in size and in distribution. And this is very interesting finding, because we wanted to improve upon those DEM tones, or dynamic element matching tones. And the first idea to do this is just, make them better matched, make your cells better matched, you get rid of the tones. But this is not suitable for this application, because if we fly the chip in space and it gets irradiated, you again get a mismatch and your tones will appear again. So that was another good finding that helps us in further development of this chip. So to wrap up, what did I tell you about today? We built the magnetometer front-end ASIC. I gave you an introduction on the test hardware that I built and simulations that I did. Those were about single event effects at the big heavy ion accelerator, and also total ionizing dose effects accomplished through X-rays. And with all of those results, we can basically say our chip is radiation hard. So how will we proceed with the developments in this? As we saw, radiation-wise, the chip is pretty much okay. So we can focus on further improvement of the performance. But in terms of radiation hardening, if it gets to the point where we really want to put it into space, we still have to handle all of those single event effects that I've shown you, and maybe improve on the total dose effects. And to do this, then we will need further detailed tests, so we can get the full response of the chip in accordance to ionizing radiation. With this, I want to thank you, and I'm open for questions.
So thank you, Raphael, for this really very nice talk. And we are open for questions, please. Okay.
I've seen here in the last sentence that you mentioned triple modular redundancy. So currently, for the current implementation, is the digital part is not protected against SUs.
Just straight once the everything.
And do you think, from your experience, this with the TMR, you can increase the functionality or the correctness of the chip?
Definitely. Especially in terms of the steps that we could see. If we have the whole integrator part in triple modular redundancy, then we will get rid of that. So for spikes, it's hard to say, because maybe they are happening in the analog, and there we can't do anything about it. And also in the functional interrupt, probably it helps, but we cannot be 100% sure, because maybe some supply line is dead, or we could not determine the exact effect where this was happening.
Okay.
I had a question. You made the simulation when an ion came from one side and penetrated through the whole part. Does it make a difference if it comes from the other side?
Yes, definitely. And it also makes a difference if it comes at an angle. So in the plot, maybe I go back to it. Here you see three different curves. The blue one is at, if it penetrates straight into there, then the angle of penetration increases. So at the green one, we are already at 55 degrees. And with this angle, the LET actually increases. So this is a bit counterintuitive. If you think of solar panels, if they are tilted, then the energy decreases. But here it is actually the length it goes through is the thing with parallels LET. So if it goes there tilted, then it has a longer length to go through there. It's close to a 1 over cosine relation. I saw in the simulation that it's not actually true, but close enough. So the thing that you asked about on the other side, you can do that, but most probably the ion will be stopped already before it reaches the active region. So you see here, this active region is buried 12.5 micrometers deep inside of the chip. Typically, a chip is like 800 to 900 micrometers thick. So if you would prolong this curve, it would rise and then stop at some point, because all of the energy is transferred and the ion comes to rest in the lattice. So with a very thin chip, you could probably get similar effects, but usually from the backside, it won't do anything.
Other questions?
Yeah.
Hi. Related to this LED profiling that you did, how you were able to characterize the chip technology? Because as you can see there in the web, the first stages are related to the metal layers.
Yeah.
So this information was available to you, or you did something to characterize this?
No, we had with the chip designer, we were working very close with them, with Graz, and they provided us with documents that specified everything of the technology of the chip. So also the exact composition and the exact thickness of those layers were given.
Okay, thank you.
Yeah, maybe one question from my side. So do you also have a look at the secondary effects? So I mean, like you have discharged particles, so energetic particles coming in, and then you have secondary electrons or whatever. Did you have a look at this radiation part?
Yes, I have it at some backups now. It's with the heavy ions and the X-rays, you don't have any problem because you don't have any secondary activated components in the lattice. But we also ran a test with protons, actually in Austria, and with protons, you don't directly transfer the energy from the protons to your lattice as you would do with heavy ions, but you have a high interaction probability between the atomic silicon nuclei and the proton. So basically they break up the nuclei and those secondary products generate the LET. And in this process, also radioactive isotopes of those secondary ion products may exist. So when we ran this test, we had to put all of our equipment afterwards into a vault that was monitored with a Geiger counter. And once it got down to safe levels, we could take it back home. Testing.
Other questions? Maybe online? No. Then maybe one, because we still have time, maybe one last question from my side. If you switch to slide 11, please, where you showed all the different effects. Yeah, that's one. And so going on the very right to the functional interrupts.
Yes.
So I see the stub functions, okay, and they reduce my outbound current. But I see also that this current from time to time actually recovers, kind of. It increases again. So like this point, yeah. How do you explain this?
This probably has to do with the exact structure of the cascaded integrated cone filter, where there's integration and differentiation happening all the time. And we could also see all the same patterns with each of these functional interrupts. So it has to do with the structure that digitally processes the values before going to the digital to analog converter. But nevertheless, we always have, like, in a time of around 10 seconds, the output current ceased to flow completely. So it's probably in the digital, but we would have to dig deeper there.
Yeah. So let's thank the speaker. Yeah. Maybe before you leave the room, Raphael also prepared an experiment. This is always very nice. So maybe you explain it first, and then you're all very welcome to join the film and have a look to it.
Yes, so I told you about the magnetometer front-end ASIC, and I've already built the application for this. It's a CubeSat Fluxgate magnetometer. I have everything up and running here with this little pumpkin. It houses the Fluxgate sensor, and all of you are invited to come here and play around with the sensor. Maybe try to find where is north, and we can have a look at what happens if you move there with a magnet.